we want to be able to calculate radiation. So we can calculate the monochromatic intensity, the energy transferred by electromagnetic radiation through a unit area. We can calculate that using this equation. Now I stands for the monochromatic intensity for a single color, and the intensity is related to energy. So this has the unit of energy. So I here for a single color is equals to the addition from one wavelength to the next wavelength of all the I's in this range multiplied by the difference of I. So basically, if there is a curve, because it's continuous, so from lambda 1 to lambda 2, we integrate it, or basically just add up all of the I inside here. This is I. And we can calculate this intensity just by adding up all this. So I at lambda 1 plus I at lambda 2, and so on for every part of this. Multiply with the difference between these two. So the intensity of this is just adding up all the I's between a certain range. So that is for monochromatic. So if you want to calculate the I for the entire spectrum, then you just have to go from, let's say, from the lowest value, say 0.01, until maybe 10 cm. And that will make you be able to calculate the intensity of radiation for the entire spectrum. But for a certain color, it's just between a range of lambda values. You don't have to solve analytically the integration. If you have the different I values, you just add it up. So it's just a list of I values, and then you just add it up, multiply by the difference between the two, the distance between the two wavelengths for monochromatic intensity. Now the unit is watts per meter square. That's what it means by energy, right? A steradian is just another unit for angle. Steradian is a solid angle unit. So electromagnetic radiation energy that the Earth receives comprises of the spectrum. And besides intensity, there's also this flux density. And there is the monochromatic flux density, or the rate. Instead of just the energy radiation, this is the rate of energy transfer per unit area with a given lambda. This is the equation. So we have the flux density. Maybe this is for the color blue or for the color red. So the flux density of that color, or the monochromatic radiation, equals to the intensity here, the cos of the angle. Now this is the incident angle. What I mean by this is, like say, for all the different angles. And we have light coming in from all angles. Where do you think is the most at this point here? From which angle does this point receive the most energy? Is it from straight up or at an angle? If light comes in from the top straight like this, at 90 degrees, it receives the most energy. So this is what we call the incident radiation. Anything that is off this incident is slightly less. So there's the angle there. So this angle, this theta variable, is this variable. So this cos is just a factor. Factor means to reduce. This is cos. So at 0 degrees, it's at 1. And then as it increases in angle, then it becomes a factor, maybe 0.8, 0.6, 0.4, decreases. So it's like a factor that reduces based on the angle. So if it's at 0 degrees, that means incident angle at 0 degrees, it's at 100%. So if it's at an angle, then it reduces. And this is the same for both sides. So this angle is from 0 to 90 degrees. Where 0 is 1 and 90 degrees, I think it's 0. Factor of 0. So imagine that this is 100, and then you times cos, which is a factor, So if it's at 100 at 1, so 100 times 1 is 100. If 100 times 0.8 is 80, 100 times 0.7 is 70. It becomes lower and lower as the angle change. And then there's this part here. What does this mean? Now, a point receives energy from, like say on Earth. Like say there's no roof, and then we are here and we receive the sun, the energy from the sun at a point. So we receive the energy from, is it just from one direction or from all directions? So we need to specify the direction of that. This d omega means the angle that is covered from the sun. But the sun doesn't cover the entire sky. The sun is just one circle in the sky. So that circle in the sky that we see is the solid angle. Okay, so like say that, and then we have a point, and then that's where we are. And this is the sky. We are in the field. Imagine that you're in the field, and we have the sun somewhere there in the sky. So this sun is covered by an angle. What we know so far is the 2D angle. If like that, then we have this. This is just a 2D angle. Now I'm going to the solid angle that I mentioned just now. But the sun is a circle in the sky. So how do we denote this angle here? We call it the solid angle. So it's something like that. This is a solid angle. This angle here. This omega. Solid angle. And the unit of this solid angle is the stir radian. For this angle here, it's just the radian. But for a solid angle like this, it's a stir radian. Now, if we measure all of this, if we think of light coming from all points of the sky, what is the total? Okay, definitely is a hemisphere, right? So, and then actually from the sun it's just one solid angle. But if like say all, just imagine that it's coming from all directions, then the total is actually a constant 2 pi. A solid angle for an entire hemisphere is just 2 pi. That's a constant for a hemisphere. So that's why here, the intensity times the angle of the solid angle, and it's bounded. That means the maximum it can receive is 2 pi. But if you just want to look at a certain angle here, then of course it's from 0 to some solid angle value. Now the difference between the intensity is just that this is watt. Let me just reiterate this. This is watt meter square per stir radian for every solid angle. This is watt per meter square without the stir radian, because it's just for a certain area here, while this one is per certain area. Okay. So there's a difference between these two, the intensity and the flux density, or just simply intensity and flux. I is intensity, F is flux. Now, I is constant with distance from source. So the intensity that comes from the sun is the same. But then you might say that we don't receive the full intensity from the sun, right? Or else we'll be burned here on Earth. The F is proportional to the angle covered by the sun. So if the sun is right next to us, then of course we get burned because it fills the entire sky. But then, since the sun is so far away, and the amount of actual energy that we receive is proportional to how much, okay, if it's close, it fills up the sky. If it's further away, then it just fills a small portion of the sky. And that distance and the angle covered by the sun is proportional to the distance. So the F is proportional to how much of the sky is covered by the sun. Now the angle covered by the sun, or the stir radian, is inversely proportional to d square, means the distance of Earth from the sun.